First, I would like to thank the organizers' invitation. My name is Jing from the State Laboratory of Quantum Optics and Quantum Optics Devices, Tsinghua University. Today I will build a talk about spin orbit coupled degenerate Fermi gas. This is the China map. Here is Beijing. Tsinghua University is located in Thailand city, Tsinghua province. Our state laboratory of quantum optics and quantum optics devices include three research divisions. One is the basic research at the application of quantum optics. The second is the quantum effect of interaction between light and atoms. The third is quantum optics devices. In scientific direction, including cavity QED, single atom manipulation, quantum coherent effect in atomic ensemble, interaction between non-classical light and atoms, ultra-cold force and Fermi nature, single molecular and ultra-cold moleculars. The outline of my talk is first to introduce the motivation of our work about quantum simulation with the ultra-cold. Then I discuss two cases of non-impacting and strongly impacting spin orbit coupled Fermi gas. Here I will focus on the strongly impacting spin orbit coupled Fermi gas, including the spin orbit coupled Fermi gas and the spin orbit coupling induced coherent production of Feshbach molecular in degenerate Fermi gas. As we all know, spin orbit coupling is a general physical phenomenon in nature. In an atom, electron rotating around the nucleus, which generates the effective magnetic field. The effective magnetic field will influence the spin of the electron, so generates the spin orbit coupling. Spin orbit coupling will induce the fine structure of energy level for atoms. In solid, the spin orbit coupling usually is very weak. If we increase the effect of spin orbit coupling in solid, it will lead to the topological insulator and quantum spin Hall effects. Let us see for a particle with charge Q moving the electromagnetic field. The Hamiltonian can be expressed as this form. Here, A is vector potential. In this Hamiltonian, the kinetic term includes vector potential. If the vector potential can be expressed with the spin operator, which represents the spin orbit coupling. Once we could construct such Hamiltonian for neutron atoms, we can simulate charged particle with the neutron atoms. Quantum degenerate gases offer us opportunities to effectively simulate the quantum condensed matter. Now we can control the Hamiltonian of ultra-cold in a number of ways. The simplest way is to change the trap potential, such as at optical lattice. Now we have powerful tools to control the interaction of ultra-cold atoms by the Feshbach resonance technology. How do we control the kinetic term? One way to exchange the kinetic term is to use the synthetic vector potential. There are already various proposals of generating spin-off decoupling, and some exotic properties have been predicted. The experiment of generating spin-off decoupling first made progress in the listed group. Our group also realized the spin-off decoupled DEC using the 1064 nanometer lasers. The Chinese, another group, also realized the spin-off decoupling DEC for USB-C group. Last year, 2 US groups also realized and started the spin-off decoupling DEC. As we all know, there are two basic particles in nature called the quarks and the Fermi, which avail different quantum characteristics. Our group and the MIT and this group also realized the spin-off decoupled degenerate Fermi gas. Now, I first briefly introduce the experimental setup and the procedures of ultra-cold Boson and Fermi mixture gases. In our experiment, we employ double mode structure. The first chamber is to use the Whipple mode, where the atoms are captured from the background of the rubidium and potassium vapor. The second chamber is an ultra-high vacuum, a differential pumping tube connected to chambers and linking time linking to order of pumping pressure. The atoms are captured from background of the wafer, then pushed into the second chamber. The cold atoms are recaptured in the mode tube. We employed a standard procedure to produce the ultra-cold atoms, including magneto-optic trap, then loading cold atoms into magnetic trap. At last, we use the radio frequency vibration tooling to get the DEC and the potassium degenerate Fermi gas. Then we loading ultra-cold atoms in a crossed dipole trap. Since the optical dipole trap provide more flexibility to the design, more complex geometrical trap potential and manipulating the spin state. The atomic clouds are detected by the time flight absorption energy. The trap is switched off suddenly at the atom clouds free effects. We detected the atomic clouds by the absorption imaging of the CCD camera. The density distribution reflects the momentum distribution of atomic cloud in the trap. Now I will give our results about non-impacting spin-off carbon Fermi gas. First, I want to show Raman process is important for generating a spin-off decoupling. If we use the radio frequency drive the transition of two ground energy levels. The spin of atoms is flipped by radio frequency. However, the momentum of atoms did not change. Since the momentum of radio frequency can be manipulated. If we use the Raman process to drive the transition of to energy levels, the spin of atoms is flipped. At the same time, the momentum of atoms also changes. From here we can see the atom achieves the momentum from the Raman process. The theta is the intersection angle of two Raman beams. If this intersecting angle is non-zero, the spin and the momentum of an atom will be coupled by the Raman process. The Hamiltonian in our work is seen as the mystical chaotic coupling. The original Hamiltonian shows the two Raman lasers interact with two energy levels. This Hamiltonian cannot be solved directly to obtain the eigenvalues. First, apply translate unitary transformation, which represents momentum of two spin states. It translates with the minus and the plus PR respectively. Thus, this Hamiltonian can be diagonalized to obtain the eigenvalues and the eigenstates. The atom can be easily projected into the individual momentum and the spin state by the Feshbach and Zhang effect. In the experiment, the general Fermi gas with the 9 half states are prepared in the dipole trap. A pair of n-pulse coils provides a homogeneous magnetic field. The Riemann we choose two Riemann sublevels as the two energy levels. When Raman coupling is at resonance between two states, the two photon Raman detuning between the 7th half and the 5th half state is about 170 kilohertz, which is one order larger than the Fermi energy. Thus, we can safely treat this system at two energy levels. Two Raman lasers are extracted from the single frequency Tysat laser.
A question? How big is the Fermi energy in the system? How big is the Fermi energy in this?
How big? This Fermi energy about energy is about several kilohertz. This detuning is about this 100. This is about 1 megahertz. This Fermi energy.
Okay.
Hard to convert units.
Yes. All of the
You said 1 kilohertz, or sorry?
No, is it 1 megahertz?
Oh, 1 megahertz.
Megahertz is the Fermi.
The Raman detuning can be precise adjusted by setting the frequency of the signal generation for AON. We first studied the Rabi oscillation between two spin states induced by spin orbit coupling. we first prepare the single spin state at the 9-half state, and the Raman tuning is at -4 ER. In this case, the zero momentum of 9-half state is at resonance with the 2 kr momentum components of 9-half state in here. Due to the spin optic coupling and the Pauli exclusion principle, the Raman coupling strengths are momentum dependent. And the atoms in the different momentum will oscillation with the different frequencies. Thus, the dephasing is naturally occur, and the Rabi oscillation will damp after several oscillation periods. Moreover, we can see the multiple features in the momentum distribution, which reflects the out-phasing oscillation for different momentum components. From this oscillation period, we can determine the Raman coupling strength. This is a critical parameter for our experiment. Then we studied the momentum distribution in equilibrium state as the case of the detuning zero. We first prepare the spin mixture, then ramp the Raman coupling adiabatically. Due to the spin optic coupling breaks the spatial reflection symmetry, the momentum distribution will be asymmetric. From this imagery, we can see smoke tail appear the different size for each spin state.
Sorry, what temperature these experiments conducted at? What temperature?
What temperature? Okay, this temperature is about 0.3 TF.
And that in microkelvin, how many microkelvin?
Nanokelvin.
TF is about 4 nanokelvin, is that right? TF, the Fermi temperature is about 4 nanokelvin?
No, the temperature about 100 nanokelvin. So this Fermi temperature about 1 microkelvin.
Oh, microkelvin, that's 4 nanoeV, 4 nanoeV.
Yeah.
Right.
With spin optic coupling, the single particle dispersion will change from the two parabolic dispersion into the two helical branches. The topology of Fermi surface will exhibit two transition and atomic density change. And notice the atomic density only Fermis populate in the lower helical branches, and Fermi surface should disjoint to Fermi surface. Then we increase the atomic density. The Fermi surface gradually emerges single Fermi surface. At last, a new Fermi surface appeared in the center of larger Fermi surface. When further increase atomic density, and the Fermis began to populate on the upper helical branches at this temperature. The quasi-momentum distribution in the helical branches can be obtained from the momentum distribution in spin basis. Here, we show the for measurement for the quasi-momentum distribution in helical branches. At the lowest atomic density, almost no atoms populate in helicity branches. The quasi-momentum distribution in lower helicity branches shows a double picture. When you increase the atomic density, the double picture gradually disappears and the fermions began to populate helicity branches.
Question. Is the geometry of this basically one-dimensional, two-dimensional, or three-dimensional?
Three-dimensional.
Three-dimensional.
Yes, but the dispersion in one dimension.
Okay, so spin-orbit coupling is just in one
One dimension. You're right.
Okay.
But the system is three-dimensional.
Okay.
As we all know, there are powerful tools in condensed matter called RPEs to study microelectron structure of condensed matter, especially for superconductor. In parallel, there are momentum reserve of radio-frequency spectroscopy in the field of particle atom to probe a single particle spectrum. Here, I will show to measure a spin-orbit coupled Fermi gas by the momentum reserve of spectroscopy. Here, the momentum of radio frequency field can be neglected. So, according to this equation, the dispersion of initial state can be obtained if we know the dispersion of final state. We first prepare the spin-nature, then run the spin-orbit coupling adiabatically, then apply the R pulse with keeping Raman coupling on. Then we plot the final state population as a function of the frequency of radio field and the momentum distribution. Then, according to this equation, we can get the dispersion of the initial state. Here we can see clear the backbinding feature and the gap opening at the steep rupture point. Here I show the radio frequency spectrum for different atomic density, which corresponds to the previous measurement in the quasi-momentum distribution. At the lowest atomic density, only atoms populate the lower branches. When you increase atomic density, atoms began to occupy the helicity branches. It's same as our previous measurement. Here I would like to mention the work spin injection spectroscopy of spin-orbit coupled Fermi gas by an IT module group. In this group, the prepares system in the single spin state as the initial state, and the final state is spin-orbit coupling. Then apply R to measure the single particle spectrum. The result is same as our result. This is a clever way to avoiding the heating by the Raman process to set spin-orbit coupling as the final state. However, our experiment prepared system with the spin-orbit coupling in equilibrium with the Now I will focus on the strongly impacting spin-off counterflow gas. In the field of ultracold, there are powerful tools to engineer interaction of Fermi gas by the Feshbach resonant technology. In applied metal atoms, the energy of two free atoms and the bond molecule have different dependence on the magnetic field. For certain magnetic fields, the two free atoms is energy degenerate with the bond molecule. So, giving rise to the Feshbach resonance. Here, I use the FP cavity in optics as the metaphor for Feshbach resonance. When the Fermi's laser is tuned near the resonance with a cavity mode, it will appear strong absorption and dispersion profile. Here we use the minus 9.5 and minus 7.5 as the two energy levels. The Feshbach resonance at the magnetic field 200, about 200 Gauss. The Feshbach molecule can be treated by granting a magnetic field from above the Feshbach resonance to the value below the Feshbach resonance. We first studied the Feshbach molecule influenced by the spin-off decoupling. Now we first try to measure the binding energy by the radio frequency spectrum. This narrow peak represents the free atoms. This broad asymmetry peak represents the bond molecules. The binding energy can be obtained from the distance between two peaks. Now we studied the Feshbach bond molecules influenced by the spin-off decoupling. We first prepare the spin mixture, then sweep magnetic field to generate bond molecules. Then we run Raman coupling. At last, we apply the radio frequency pulse to dissociate Feshbach molecules with keeping Raman coupling on. This is our result. Spin-off coupling will induce the narrow of binding energy. This phenomenon can be understood from the dispersion. When we increase the binding energy, when we increase the Raman coupling, the dispersion of free atoms will move up. This is of the low helical branches. In parallel, the dispersion of free atoms will move up. Now, thus, the binding energy of Feshbach molecule becomes narrow by the spin-off coupling. Now I will discuss the spin-off coupling induced coherent production of Feshbach molecule in degenerate Fermi gas. We first assume coherently produce S2 Feshbach molecular from fully polarized Fermi gas, because this final the wave function of final state includes the singlet state. Here I want to understand by the original Hamiltonian. This is a single particle Hamiltonian. This is two atom Hamiltonian. We can rewrite two parts, the symmetrical part and anti-symmetrical part. And anti-symmetrical part represents the transition from the triplet state to the singlet state. If two Raman laser propagate in the same direction, the anti-symmetric part becomes zero. If the angle of two Raman laser is non-zero, anti-symmetric part will induce the Feshbach molecule from the fully polarized Fermi gas. Here I would like to mention the work in the junior group about the strontium quark. Can be understood by our theory. In the work of probing interaction between output fermions from single spin state, the Hamiltonian is seen as our spin-orbit coupling Hamiltonian. The only difference is one photon momentum is transferred. In our Raman coupling, is the two photon momentum is transferred. Thus, even with homogeneous orbital, there still is the S-wave interaction due to the spin-orbit coupling. When increase the trap potential, the spin-orbit coupling term will give small contribution to system. Thus, the spin increase the trap potential will decrease the interaction. This effect can be called the strong confinement effect, or named the energy penalty effect. In our experiment, we first prepare the single spin state as in the minus -1/2 state, and the Raman detuning is set to the minus binding energy. Then we measure this Feshbach molecule by the reducer as function of the duration time of the Raman pass. For the 180 degree, the population of the Feshbach molecule is very large, and the coherent Rabi oscillation can be seen. For the 90 degree, Feshbach molecule, the production of Feshbach molecule is decreased a little, but the Rabi oscillation became invisible. For 0 degree, there are no Feshbach molecule is present, which means this single spin state it prohibits transition to this S-wave Feshbach molecular state. We moreover measure the population of Feshbach molecule and scattering atoms at the -7 state. We can see their significant Feshbach molecule at the frequency of large relative tuning compared to binding energy.
Question. The Feshbach molecules are bosons, are they?
Like a boson,
So
you're right.
can you reach a temperature at which they will condense?
In here, not dense.
What would the Bose-Einstein polarization temperature be
In here.
in this situation? Yes.
In here, if we now we temperature is about 0.3 TF. If we can reach the 0.1, this can reach the molecular basic density.
I see.
Yeah. Now we little high in the critical temperature.
Do you think you'll be able to cool that low?
Sorry.
Do you think you will be able to reduce the temperature that far in the future?
In our system,
Yeah, do you think you will be able to attain such low temperature?
yeah, if we do not add the Raman coupling, the temperature can reach. Because in our system, the temperature is little high due to the Raman coupling.
Oh.
Yeah.
But that's a catch-22. You want to have the Raman
Now we can try another way to avoid this Raman coupling and avoid it in Raman. Yeah. Here, for 0 degree, you can clearly see no Feshbach molecular created in this Raman tuning. Okay. At last, I mentioned the work about Raman-induced Feshbach resonance in a single component from a gas. This work in the listed group, which is the same as our measurement of the being of the coupling induced resonance between the atom and the molecules. In this experiment, they fixed the Raman tuning and measure the atom loss as a function of magnetic field. The maximum atom loss corresponds to our spin of the coupling induced resonant transition between atom and the molecules. Conclusion, we studied the non-impacting and strongly impacting spin-off the coupled Fermi gas. We also developed two related technology about Raman spectroscopy instead of the radio frequency spectroscopy and the optical control of Feshbach resonance. Okay, at last, I would like to thank my group members. We also have a happy cooperation in theory with many groups. Yeah. Okay, thank you for your attention.
We have plenty of time for discussion. Any questions? Yes.
So, is lack of spatial inversion important to create this hybridization between single and triplet molecules? Is to hybridize single and triplet molecules, is the lack of spatial inversion important? So E equals to minus P?
This is also important. Yeah. So here I think the important conclusion in our experiment. Spin-off decoupling provides the finite matrix element between the singlet and triplet, therefore implies the bond molecular system with spin-off decoupling have the triplet even component which can be in topological.
I think in analogy with solid state.
Solid state.
You can have spin-off decoupling without lack of inversion symmetry, but then you want to mix singlet and triplets there.
Yeah,
It's the same here.
It's same. Same idea.
Yes.
So this is in a system where the population is the same, right? There's no population imbalance between the two lower states that you consider.
In this here.
Yeah.
In here.
Half states.
Yeah, depends what are we doing. In here, we first prepare the spin polarized Fermi gas. This is no acid interaction, only the period. Yeah.